Assalamu alaikum. Questions from last time? Comments? Issues? Project notified or not yet?
الانجينير اليوم كان امس كان تعبان فكسر
What?
قال بينزل
امس كان تعبان كسر لبات الاسبوع لانه تعبان فقال الاسبوع الجاي لكن هذا الاسبوع حيرسل
هو الخميس اصلا
Okay. So you didn't have a lab this week? Yes?
Girls and boys didn't have a lab.
What?
All of the boys and girls.
Cancelled. Allahu Akbar. Good. Okay. The quiz, I will correct the quiz tonight or tomorrow. Inshallah. Tomorrow. صحيح tonight. There are 2 tasks before the quiz. Okay, so tomorrow, inshallah, will be ready. So what else? Do you want to do another quiz?
Yes.
When?
After the vacation.
After the vacation, you have the midterm, right? Don't know. Check. When is your midterm?
Next week.
The midterm is next week. Yeah, for this course, أكيد يعني. This I think. 22 is it? 22. Okay. So if it is 22 and the week after is a holiday, right? 23 is a Thursday. مش عارف يكون هذا Thursday. The week before is the vacation. It's good so that you study properly. Okay. Or the week before. Guys, wait. So 22 is the exam. It's here recorded. Okay. This week is off. Okay, that from 12 to 16. So if you want a quiz, it has to be next Wednesday. Only. I have no other options. You have a midterm next week?
On Thursday.
You have a midterm on Thursday? So you have a quiz on Wednesday. Normal نكون عندكم quizzes. حدا لك سير الكهرباء. It is senseless, okay? يعني to make it on the 20th وبعدين on the 22 you have the midterm.
كنت دارسين بالفاكيشن فلو فتنا كويز midterm يعني كنت دارسين
استعداد. دكتور غلط الكويز ولا غلط الميدتيرم.
انا بخاف انكم تغلطوا بالكوز وتكتئبوا.
لا ان شاء الله لا. حط نفس السؤال.
It could be online.
No, but no.
1 minute.
No, online it will be impossible to solve. Okay, guys, the idea of the quiz is that I want you to study so that you practice. This is the concept of the quiz, okay? So to make it just before the midterm, I don't feel it is needed. So this is what we agree. So next week you don't want a quiz on Wednesday. Anyone wants a quiz on Wednesday? Next Wednesday, you want quiz? 1, 2, 3, 4, 5, 6, 7, 8. Who does not want a quiz on Wednesday? Okay, more. Okay, good. That's okay. We will not make a quiz next Wednesday then. Okay, so when it will be?
29.
Or 20, 29? Yeah, 27. Come on, what will be the material? And even it will be 22 or April. Who wants 22? 22 just before the exam to have a quiz. Shoot 21. But this is what I'm saying, 20. Before the 22. 22 is the midterm. So you want 20 to have a quiz? Who wants 20 to have a quiz? Okay, 20 it is. Okay, 20. So the material will be I will let you know later. Okay. Well, for emails, everything that we will see. Questions from last time? No? So let's make a small review, and I will review with the different colors. Guys, yes. Okay, good. That you asked. Okay. So, guys, so last time we started here with this chain, and I commented to you about the channel encoder and the interleaver, both of them, so that you help the receiver to deal with the noise. I explained only this one, and I told you that these are you can self-read because they are not on the course description. Here we explained how we will do it. This one, the easy one. And then here your colleague is asking about felt data rate to required data rate, right? So what is the difference between them? So here, what was it? Whenever we have more repetition, so more bits are transmitted. So instead of 7 repeated, okay, or 21 repeated, what will happen? You will need more time to download. So instead of you click the image, okay, instead of seeing it directly, it has to be downloaded 7 times or 9 times, then you can see it. So what will happen? You will feel it is slower, the data rate. So you will complain about Ooredoo service, say, well, I have the service, bad service, okay, because I feel it low, the data rate. This is what is the felt data rate. So this is the measured data rate that you can have at home. But on the other hand, if you are a designer, you have to design for the system to support more data rate. How? If to download one image is 1 Mbp, you need to download it 9 times, so you need 9 Mbps. So you need more data rate. So this is what we call required data rate. Answer? Clear to all the difference between them, felt here and required? And then What is this? Ah, yeah, the distribution of the noise is needed because your system could be dynamic, okay, written here, but switching between different applications. And we started with the interleaver. So what is the idea of the interleaver? Good here, distribute the bad stuff. So it's about sharing, okay? So what is here the idea of sharing? And I see that I put, well, you know that whenever we send bits, yani, but here it is just to make it easy. So ones here, or twos, or threes. If we send them without interleaver, here we have a bad channel here. Here we have good channel, here we have good channel. So S1 is properly received, S2 properly received, S3 0. Good, so S3 lost. Then they thought, we don't need to have it fully received. If we receive 80%, 70%, the channel encoder will help us, right? If the channel encoder will help us, then we can we redistribute this bad stuff overall? So here we receive 70%, 70%, 70%, and then we receive everything. So the idea is now this interleaver, we redistribute. So instead of 1111 altogether, we will send part of it here, part of it here, part of it here. The same for 2 and the same for 3. Here we have good channel, here good channel, here bad channel. So the good channel, everything will be received. Here everything will be received, and here everything will be lost, as we already know. But now notice that for the first symbol, the first 2 parts received, the second 2 parts received, and these ones lost. Here we receive like 70% correct. With a channel encoder, with a proper channel encoder, we can recover S1. So here S1 received. The same for S2. Some part received properly, some part lost. With channel encoder, we can receive it properly. For S3, notice that some part will be received properly, some part will be received properly, and some part lost. Now S3 can be also received. So without interleaver, we have 2 symbols received, 1 symbol out. With interleaver, we have the 3 symbols received. If we go bitwise, let's say 70% received here, 70, 70, 70. But thanks to channel encoder, we can, out of the 70, we can say here, we can recover what was the original sequence to be sent. Clear? So the interleaver, first conclusion, cannot be used without channel encoder. It is useless. It will do nothing. Okay? Because of the channel encoder and because of this property of the channel encoder, it can fix some of the errors. Okay? Then the interleaver was introduced. And the objective of the interleaver is to guarantee that everything is received, regardless if the channel is good or bad. Questions?
So this is only for the equal number of bits for the samples?
Again?
This is only if the samples are equal bits, have the same bits, like 6 bits.
Yeah, whenever we apply channel encoder, we apply channel encoder for not one, it's not per bit, okay? It is per chunk. So it is impossible that you will have symbol 1 with a different encoder that's symbol 2 than symbol 3.
What's the situation where this could happen, where there's 2 good channels and 1 that's not?
Yeah, in that case, okay, we have to be aware, okay? Because here, in order to do that, you have to sense the channel before transmit. So here, you will sense that you have a bad or good or good. In case you have only this is good or both of them bad, if you do this, the 3 will go down. So you will say, okay, I will save this one and the other 2 will die. You, as an engineer, you are the one who will decide to do interleaving or not. Okay? But yeah, it is another tool that you can use and maybe it is useful. Good? Clear this one? There is another advantage for the interleaving. Do you see it? No, it's exactly the same. So here 6 or 6 or 6. I'm trying to do the same, just scrambled. Sorry?
Could be faster?
No, again, here I have 18 bits. I transmitting 18 bits with interleaver, without interleaver. So it is the same. Obviously, this is the first advantage. So the first advantage here, advantage for the interleaver, less data loss. Good. This is whatever we have seen. I'm saying that there is another advantage. Do you see it? Ali, you are with us? Sure? Okay, good. What is the other advantage, Ali? Amir, do you see another advantage? Hamza?
You consume more data.
No. Hamad?
Let's remove the unknown bits.
No. Hisham?
I guess maybe the coding is not complex, like you are taking only two.
Yeah, definitely. Here there is advantage. There is no disadvantage. So this is pure engineering. Okay. So yeah, but I need one more advantage.
We can detect the error.
Faiz, Muhammad Faiz, right?
We can detect the error signal.
No. Okay. So the idea of the interleave, Muhammad.
Could it be that it doesn't increase the bit rate required?
What?
It doesn't increase the required bit rate.
It does not. Yeah, definitely. But yeah, this is not an advantage. So here, what is the other advantage? Maybe it is somehow hidden, but this idea of the interleaving is the basic idea for encryption. What is the story? Here, imagine this is the sequence for user 1, sequence for user 2, sequence for user 3. There is a hacker who wants to hack this info. How you will protect this info? You will scramble it, okay, all over. So if here without interleaver, the hacker, if he is able to decode your sequence, he will get all the sequence. But now, if the hacker will do it here with interleaver, okay, it will hack your data. He will understand nothing, okay, because it will be some part of this, some part of the other, some part of the other, and he will not know how this has been scrambled, okay? This is the basic idea of protection against hacking. Okay, definitely current systems, they are more complex. One bit from here, one bit from 7 samples ago, or 7 samples later. Just there is a protocol to mix them up. Okay, but yeah, it is a mix up. Okay, so that not all the data for the same user is all together. Good. So here another advantage. It will provide more protection, against what, hackers, let's say. Yeah, hackers.
So here with you have to you must have an encoder to decode the scrambling you made with the.
Yes.
Isn't this like the way of or the order of the scrambling you made isn't sent with the same information? So can the hacker just access the same part also?
I don't get your question, but whenever you do anything you do at the transfer, you have to reverse it at the receiver. So you did a scrambling and the transfer, you must do a descrambling at the receiver. So the technique that you agreed to do at the transfer, the receiver should know it so that it can reverse it. Otherwise, it will not. If the hacker is able to steal the information that you connect to the transfer whenever you are the receiver, whenever you are telling the receiver, this is my protocol, definitely you are dead. This is the idea what was implemented years ago. It was in Second World War. Do you remember what it was the name of that machine? Enigma. Okay. So the German one, okay, they were not communicating because they said maybe the communication itself is stolen. So whenever they want to put a receiver, they were calling the submarine, okay, that come back to Hanover, okay. We will update the receiver so that whenever we will send it later, no one can read it. Okay, clear now? More questions? Sure. We don't teach you here any course about hacking, right? Cybersecurity as an elective course, yeah, maybe. But yeah, you have enough background to go and dive, okay, online and be a professional hacker. Ethical hacker. Oh, but I don't know. You decide. Okay, clear. This is like everything. Okay, so your studies will enable you to become an engineer. I always say that whenever you graduate from here, you are not engineers, but you are ready to be an engineer. So whenever you will go and you work, okay, you will become an engineer. Good, but you have the background, and the good thing about this program is that we teach you from every place. Okay, so you can work as a power engineer, you can work as a communication engineer, you can work as a biomedical, you can work as a computer engineer, you can work as a mechatronics engineer, and everything. Good, but in every place where you go, you have to learn more. Good? Clear? Abu Asal. Abu Asal, answer. What do you think? Hmm? Abu Asal. You can leave if you want. You don't want to leave? I want to talk to you after class, okay? Questions? No? Okay, so we will see now a new section, okay? One of the largest in the whole course, okay? It's called the modulation, which is, where is it? We have the chain, right? Yes, this one. So the modulation.
There are no disadvantages.
No disadvantage. For the interleaver, it's a pure engineering development, so it comes with no disadvantages. There is nothing to say, well, I have to trade. So for the modulation, and in the book, there are so many modulation techniques. There is one called PAM or PPM or FSK, and there is one called PSK QAM. So I have not explained what is modulation. I will explain, but just to put you in perspective, okay? So this is the one that is interesting for us. Why? Because this is the one that is now in 4G, 5G, Wi-Fi, satellite, everything that has large data rate. This is the only modulation that is used. So why we explain the others? Because maybe you will need to implement them on something that is low data rate, and I will put examples, okay, as we will explain them. But yeah, these three I will briefly explain them. This we will deeply explain it. Good. Again, just for the sake of usage. So let's say for 90% of the systems in the world, this is the one that is used. Yeah, but there are others, 10% that are the others used. It is worth to study, yes. It is worth to see what are they or when they can be useful, yes. Okay, but I will not dive. Okay, so problem why? So if you read in the book and there are problems, okay, at the end of the chapter for these, don't solve them. Okay, they are for this one, yes, solve it. Good. Yeah, there are systems here in Qatar using these, yes, and I will comment on them. Okay. So first of all, what is, so this is just for you whenever you will read in the book, okay? It is, well, especially the book is a mix up, okay, of techniques. But yeah, this is the one that we are interested in. So first of all, what is modulation? Okay, we have not seen modulation before. So what is the meaning of modulation? Whenever they wanted to send, you know that we have bits, right? Zeros, ones, and so on, that you want to send. They realized that can't we mix, or not mix, okay, add bits before sending? What is the idea? Now, if I want to send, let's say 1, 2, 3, 4, 5, 6, 7, 8. 8 bits, okay? I will send the first, second, third, fourth, and so on. They said, is it possible to combine these bits and send them together in one shot? Okay, so instead of one bit in each sending, okay, can I send 2 or 4 or 5 or whatever? So this idea to combine bits into one single transmission, this is the idea of modulation. So by definition here, modulation is combine bits for transmission, So how to combine bits? We studied bits, so the system is digital. So here, this is modulation. Modulation. This is the unit. The input are bits, okay, that come from the source encoder, will channel encoder, will interleaver. Then they will enter into the modulator. The output of the modulator, they are not bits anymore. They are symbols. Okay, be careful. Samples, this is not equal as symbol. So here, sample that we saw in sampling, okay, it's not equal to symbol. Symbol is for modulation. Good. So what is the idea of the symbol? The symbol is one or more bits together. So how can we put one or more bits together? through modulation, through these different techniques. Now, is it good to put more than 1 bit per transmission? This is actually the idea of everything that we have now in data rate. 20 years ago, data rate was in terms of kilobit per second. Why now it is 10 megabit to 100 megabit to 20 to 200 megabit per second that you can get from Ooredoo? One of the main reasons is modulation. Notice that before, all older systems, they were transmitting 1 bit. So each transmission is 1 bit. Now they can transmit 5 bits per transmission. So what happens to the data rate? 5 times more. 10 bits per transmission, 10 times more, and so on. So every time they are able to increase the number of bits, the data rate immediately doubling. Okay, so that one of the main reason again why we have a boost in the data rate comes from modulation, because now we can send previously 1 bit at a time. Now we can send more. Okay, and this symbol we will see especially here can be dynamic. Okay, so our systems now, they are very effective, and well, this one does not come for free. So yes, we can increase the data rate, but we will have some issues, and the systems are dynamic. Okay, so at the receiver side, it's like a gift. Each time it will open the symbol. Okay, sometimes it will find 2 bits, some others 10 bits, some other times 1 bit only, and so on. So it is a continuous adaptation. Okay, the system is dynamic. We will explain all of this. But so far here, the idea of modulation is we want to combine bits. Good. How to combine bits? The first approach is, this is the idea of PAM. So here PAM stands for pulse amplitude modulation. Keyword amplitude. Okay, used in practical systems, yes, old ones, but yeah, still used. What is the idea? We differentiate between the symbols in terms of the amplitude. So I will do it like this. So here, this is capital T over time, and this is like shouting. Okay, so if I want to send symbol 1, I will send it with a power of 0.25 watts. Symbol 2, I will send it with a power of 0.5 watts. Symbol 3 with a power of 0.75 watts. Symbol 4 with a power of 1 watt. So you as a receiver, if you receive the signal with 0.75 watts, you know it is S3. You receive it with 0.25 watts, you know it is S1, and so on. Okay, so here why I say it is like shouting. So whenever you increase your voice, okay, you are angry, so you want to say something. Whenever you are whispering, you want to say something else. Sometimes even for the same word. Okay, especially in Arabic, we have some very nice word. Okay, Habibi. Okay, it's not the same Habibi or Habibi or whenever you are shouting. Okay, it is even the same word. Okay, but yeah, say it with different accent or with different tone, it can mean something different. Have you ever realized this? Okay, good. Yeah. Next time, whenever you will fight with someone, you will see that most probably the first one is used. Okay. So the idea here again, okay, is by having more power, more amplitude in the signal, it will mean something different. Then here, what are the bits? We said that we want to transform bits into something to be sent. Imagine this is the sequence of bits that I have. Good. And here I decided that I have 4 different symbols, S1, S2, S3, S4. Okay, so if there are 4 symbols, then we can make the first one to be 0, 0, the second 0, 1, the third 1, 0, and the fourth 1, 1. So now here, whenever it is 0, 1, this is S2, 1, 0, S3, 1, 0, S3, 0, 1, S2, 1, 1, S4, 1, 0, S3, 0, 0, S1, and so on. So whenever I have them like this, what will I transmit? This is T. So S2, 0.5. So here, this is 0.5, or this is 1. So I move easily. Okay, so S2, then S3, again S3, then S2, then S4, then S3, then S1, and so on. So here you see this is S2, S3, S3, S2, S4, S3, S1. So this is whatever I will transmit. Just I increase and decrease the amount of transmitted power, and the receiver, whenever the receiver will receive this amount of data, this signal, it will say 0.5 watts. This is S2. S2, I know, this is like a table, okay? I know that S2 corresponds to 0.1, then the receiver will know. And notice that here, instead of transmitting 1 bit at a time, how many bits I'm transmitting at a time? 2. So now I'm just immediately with this easy approach, I'm doubling the data rate. Okay? So here again, instead of transmitting 1 bit at a time, I'm transmitting 2 bits together. Okay? By transmitting S2, S3, S3, and so on. Do you want to increase more the data rate? What you will do? The number of possible symbols. So instead of from S1 to S4, you will make them from S1 to S8. So from S1 to S8, but yeah, we know that the maximum is 1 watt. So they will be from 0 to 0.125 and so on. Can you make them 16? Can you make them 32? Yeah, less 16, yes, to 32, no. You can make them any number you want, okay? But what will be the challenge? This is good. This is not a challenge. The power is maximum 1. So you will, this from 0 to 1, you will divide it into 4, 8, 16, 32, and so on. What will be the problem? At the receiver side? Yeah, the receiver side can make a small mistake, okay? If they are close to each other, the probability of mistake will be large. So here, increasing the number of possible symbols will increase the data rate. This is good. But also will increase the probability of making mistakes, probability of error. This is bad. Hamza, you were raising hand before, right?
So what's the difference between this and Hoffman code?
Hoffman code, that was from samples. So it's different.
But you're combining bits together.
Hoffman code, we have samples, okay, and we were trying to find what is the best representation for bits for them. Okay, now here we have bits and we are trying to find what is the best way to transmit them. They're not the same. And even here for the Hoffman, the input were samples, the output were bits. Here the inputs are bits, the output are symbols. So if you would like to look at Hoffman, maybe we are doing something reversal. We are transforming in samples into bits, here bits into symbols. They have nothing actually related to.
And there will be voltage loss between them?
Sorry?
There will be a voltage loss, right?
Voltage loss? There is no voltage loss. So this is a value that you will decide. There is nothing to be lost. So here you will decide to transmit with 1 watt, with 0.7. So there is no loss at all.
This difference from quantizing.
Has nothing to do with quantization. Yeah, the idea of intervals and so on, yeah, it is the same sense, okay? The same sense of engineering, okay? But the role of what is doing this one is completely different.
We change the amplitude 2 times then? We do it one in quantizing, and then here.
Yeah, definitely. You can do so many stuff on the signal. So whenever the signals comes from here, something will happen to it in the sampling when the source encoder or channel encoder, okay? And here we can add more bits. So here cut more, and here introduce some error. Yeah, definitely. Every box will work independently of the previous, okay? And if you will work in the development of something like this, okay, it will be the approach in engineering is called black boxing. What is black boxing? So you are an engineer working in modulation. You have no idea what's happening before. What you will say, I am the engineer here, previous engineer, give me the sequence of bits. Well, that's it. Don't tell me it is video, it is image, it is quantize, I don't care. Okay, I need only bits here, and I give you symbols. Here, the one working in multiplexer, he will have symbols, users. Here, the one working for the channel encoder, bits. Everyone is doing his work independently of the others. Okay, and this is what we call black box. Why they followed this approach? That's it. There is an error in the system. They will go and they will cannot check everything from zero. Okay, they will say, engineer working modulation, do your work, double check here, and so on. So to find an error, it's much easier. Okay, or to have an engineer working here, you need an engineer doing modulation. So it is impossible that he will be aware of everything. Okay, he will do only his part. Good. So to make the work to be sequential and working properly, we need everyone to work independently of the others. And there is a supervisor that will have knowledge, okay, on what's going on. Is the flow correct, not correct? And whenever there is an error, he should immediately know where is this error coming from. Good? Clear?
The board, like the values, do I have to choose it or everyone can? Is there a standard for the board values?
Yeah, for sure. So anything that is in communication has to be standardized, okay? And whenever you will do something, you will always try to follow a standard. Why? Why you always we always like standards? So that any other receiver that you will buy from Amazon will work. Okay, so it will make your life easier. Okay, you want to complicate yourself? There is something called proprietary. Okay, so whenever you have this, that you will do it yourself for yourself. Okay, and it will not work with anything else. Whenever you have a system that is controlled and it will not increase, okay, you will do this setup. You will have more control of what's happening. But yeah, you have to do everything from scratch. Good, but yeah, we always try to follow standards. It will make our life easier. Delay? No. You will have a larger table to select, but always you will select one. So one at a time you transmit. Okay, you cannot transmit more than one at a time. Okay, so this is happening at the transmitter. At the receiver, what do you think that will happen? Salah. Usama. Usama. What was the question? That's it. What will happen, Hamad? Ideally, yes. Practically, this is what is received. Good. Why is that? No, yeah, there is noise, interference, and so on. What is the problem with the setup? Whenever you receive the red one, what do you think that might happen? That's it. The power can jump, okay, or can decrease. So here, maybe you have transmitted S2, but because of the high decrease in the power, let's see here. Let's put some of them. So here, this one, for example, definitely you will think S1 has been transmitted. With this one, you will think S1 has been transmitted. With this one, you will think S4 has been transmitted. With this one, you will think S2 has been transmitted. So you will make mistakes. Okay. So this is the problem with this setup. Here, this setup, okay, there is a probability to make mistakes at the receiver side. Okay. This is because of the amplitudes. Good point.
Do we use a clock here or no?
Just a minute. Okay, so equalizer, rectangle. So that I go back to them. What?
Do we use a clock here?
Do we use a clock? The system has to be synchronized, definitely. So here, this is first sample, second sample, third sample, fourth sample. Yeah, sorry, symbol, and so on. So the system, every system in the world, yes, it works with the clock. But yeah, it is not suffering from the problem of the clock. We will see the next scheme, which is this one. This one will have an issue with the clock, issue with synchronization. This system has no problem with synchronization. Okay, so here, the problem for this system is the power level. Not only that, if here, imagine that I want to transmit the signal with the highest power, 1 watt. I am shouting here. You are hearing me here and that I'm shouting, right? Someone outside will hear me shouting? He will hear it much less. So he might think that this is the whatever I'm sending, right? So here we have the issue that this is the transmitter. It is the signal will not be received the same as receiver 1 or receiver 2. Why? Why, Hamza? Distance. So here, the distance to the first user is not the same as the distance to the second user. So different distance. Whenever I have higher distance, this is like whenever you call a friend, okay, and he is away or he is close. Whenever we have more distance, we have more loss of the power. So this is called path loss. Whenever you have path loss, you will receive less received power or energy. And then here maybe you will transmit 1 watt. Here at the receiver, you will receive 1 watt, but here maybe you receive 0.3 watts. Good. So the signal that here, what was 1 watt? S4, you will send S4. It was S4. What is the one with the highest? Yeah, S4. So here, you will transmit S4. User 1, receiver 1 will receive S4. Okay, you are good. But here, this one will receive it as S3, 2. Then you made a mistake. And you cannot control the distance of the receiver. Example, this is the cell of Ooredoo. Here we have the tower. Maybe the user is here, but maybe the user is here. Not only he will be fixed, maybe he's moving with the car. So he is far, then close, then far, then whatever. Good? So the distance is something that usually you don't control. Which means this problem will suffer. This modulation scheme will suffer. Is it clear? Anyone lost? Hamad, your colleague. His, we want the colleague. He's good, كمان. Your name Abdullah, صح؟ الكاب هاي يا بتحطها لورا يا بتقيمها. لأنه مش شايف عينيك.
عشان اللمبات. هيك كويس؟
شوف ارفع ثاني شوي.
نعم.
ارفعها ثاني شوي. ثاني شوي. هيك good. Questions? Hani, you follow us? Sure? No issues? I forgot your name. No, مش محمد اللي وراه. محمد ايش؟ محمد حسن صح؟ Yes, محمد حسن. What you said before as about the equalizer?
So we probably send like a test signal to see the distance.
Very good.
I know a lot about the
Where you got this information from? In the music. شايفين الميوزك good. Okay, good. Okay, so what is the story here? Okay, good. If you are able to know the distance before you transmit, this is what he said, that you send a test signal, okay? So here I have user customer 1, here I have customer 2. If before transmitting, I can send a test signal, okay? And the system actually does that, okay? So whenever I will send a test signal, I will know that this guy is close, this guy is far. Not only far or close, I will ask about how much of the data is lost. Coming back to my example here. So if I know that how much here is lost, 70%. So if I want here the signal to be 1 or close to 1, instead of 1 watt, I will transmit 3 watts. I will increase it before transmission. If I send 3 watts, I will receive 0.9 watts. 0.9 watts, the receiver will receive it properly. Good. So this way, so here, to compensate the distance or the path loss, okay, or the path loss, to make it any more engineering, Okay, we can use an equalizer. So what is the equalizer doing? Checking before transmitting about how much is lost and compensating before transmitting. So the equalizer will, the word it's called pre-compensation. What does it mean pre in English? Before. So before. So you are applying a compensation before the problem to happen. Because you know how much will be the problem. Ask him. Oh, someone was raising hand here. Whom?
I was saying like if the distances keep on changing, so equalizer will keep on sending the test signals?
Yes. So this is why we need to set what is the they call it periodicity. So how much the equalizer how many seconds it should recheck. Okay. So the faster it can recheck, the more accurate will be the system. Okay. In 5G, for example, the system rechecks each 1 millisecond. Each 1 millisecond, the system rechecks. Is it possible that we move in 1 millisecond? 1 millisecond, yes. How much will be the car movement? Guys, the system, the standard is defined 1 millisecond. So why they will do it like this? Yeah, but who can move in 1 millisecond? What? When we want to send a signal to the light, to the infinity and beyond. Yes. Sound. We want to send the signal to the guys. Satellite. Satellite. Okay. يعني بطاط. Okay. Flying object. Okay, good. UFOs, no, they will not communicate to UFOs. Okay, good. But can we provide coverage to airplanes? Yes. Now, yes. Okay. Now with 5G, yes, we can provide, and it is exactly the same tower that we have here on top. Okay. Here we don't have on top of this building, but yeah, on top of the female building or on top of the library, you have seen it, the tower. So that tower, okay, usually it is like this. Okay, and the antennas are inclined down. Why they are inclined down? Then we are down. Okay, so where are the customers on the street? Okay, so whenever now they want to provide it for planes, they will do it like this. No, it is not pointed at all because they don't know what is the plane. Plane can pass. They make it no pointing at all. Okay, so they will do it like this, and it is open. But yeah, it will cover a good area. Okay. Okay, so this is the first issue. Second issue, high-speed trains. Okay, high-speed trains here we don't have, and we don't need actually. Okay, but yeah, in large countries, okay, they have high-speed trains, and 5G will still cover people inside the train, and the train is moving at 400 kilometers per hour. Good, and the internet works without an issue, perfectly good. What else? Okay, we could be in an environment that the environment changes, and here we have one. Okay, that is giving headaches to our engineers. Okay, where is it, يا محمد حسن؟ حسيتك بتهز راسك يعني. Where? Where? What you said? BCR. هو والله BCR يا تزهدك. Yeah. You know that you are moving to the new building, right? 5 years. And I joined Qatar University 2012, and they told me this is provisional office. Next semester you will move. No, today they start moving. Okay, but I tell you that you will regret moving. Yes, you will see that here is better. But yeah. خبصوا كتير أشياء. Okay, I don't know. It is recorded, guys. So we will see what happens. Okay, next semester. coming back, where we have here an issue, okay, the issue is in Daphne area, okay? So many towers, so many signal reflections. So they have tower here, next tower, next tower, next tower. Some of them glass shape, okay? Some others, the front, I mean, okay? Concrete, some other mix up. So whenever they put here an antenna for transmission, it will do like this. Reflection over the glass. And here another one, and another one, and a car moving, okay? It is a very dynamic area, okay, during the day, with so many reflections. So you, without moving, you stand there, okay? You check what is the signal received in your mobile phone, and it is changing all the time. The signal changing all the time, you are stand still, okay? Even you can ask the people in the room to be quiet, no one to move. You start measuring the signal changing. Why? Because so many reflections, and your signal can come from so many places, okay? This is why the engineers that are working for this area, they really suffer. Okay, and we have a new tower building here. Now they put the glass outside. Now they removed. They do everything that change. They need to reset up everything. Okay, so that area needs an equalization of 100 millisecond timing. Good. What is the challenge in general for the equalizer? Complex. Okay, it is complex. You have to check each time. We send the test signal. Or tell me how much you receive from the test signal, your receiver. Okay, well, then I can adapt and so on. So here, this compensation or equalizer, its main problem is complexity.
Is it not causing a delay to the signal actually?
But yeah, that delay is extremely minor. Okay, they design it to be not noticeable. Good, clear. So yes.
So hopefully, like for every device, there's a test signal sent to each device, like million of users.
You will be amazed. No, it's not only one test. So later, whenever we will study the multiplexing, where is the multiplexing? I saw it today. After the modulator. So here, whenever we will study the multiplexer here, you will see that whenever you would like to make a WhatsApp, you want to send a WhatsApp, they will give you one slot in the multiplexer, okay? But whenever you would like to download something, one slot is not enough. So they need to give you 4 slots, okay, or 8 slots. Then they need to do testing on each one of them. So not only for each one they will do testing. Some people, they need to do 8 testing or 12 testing for the same guy because he is using more than one slot. Good? Clear? All fine? Can we move on? Okay. So let me recap. So for this spam, we have it in terms of the amplitudes. I put something here before, right? Equalizer. Good. Oh, good. This one. We said that this is the way to transform bits into these symbols. This is how we will transmit in black. The one in red because of the noise and the distance. Okay. So it will be a challenge to deal with it. Equalizer can solve. It's good to write it here. Equalizer can solve distance or the path loss, but it cannot solve noise. So the noise that is received, you can do nothing with it. The equalizer cannot fix it. Okay, the equalizer only for the path loss. Good. So there will be still a probability of error. Increasing the number of symbols will increase the data rate. This is good, but also will increase the probability of error, regardless if you use an equalizer or not. Cool. Is it always needed, the equalizer?
Very short distances, I guess not.
A good point. Very short distances, maybe not. But I have something better than very short distances. Like? Sorry?
Homes or
You come close, okay? Whenever it is, this is for, I'm talking about wireless, but whenever it is wireline, okay, the internet that you receive at home, wireline, right? And the wire, it is the same if you connect to, how much we said before, 1 kilometer or 3 kilometers. It's a cable. So in that case, you don't need an equalizer. The equalizer you will need it whenever you are 100 kilometers and so on. Cool. Okay. So coming to this rectangle that I forgot. Okay. So if I want now to put this, notice that I have drawn here rectangles, right? What are the rectangles? Like here, the amplitudes, right? So this one rectangle. So here, this is a rectangle, this is a rectangle, and so on. So if I want to put it mathematically, the different symbols, so S1 of t, I will say it A1 multiplying G of t, S2 of t, A2 G of t, S3 of t, A3 G of t, Sm of t, M G of t. So what is this G of t? It's like the basic building block. So the G of t is this one. Okay, capital T we put. Yeah. So here, this is the G of t. And whenever I want to send S1, I will multiply it by 1, by 0.75, by 0.5, by 0.15, by whatever value you want. So this will be the amplitude. This is the amplitude. Oh, this is the shape or building block, I call it, right? I call it the basic building block. So coming to this G of t, as you saw, it is a rectangle, right? And we will provide what is the amplitude for it, right? Okay. This rectangle in a practical system, if you want to see its response on the frequency domain, how it will look like? You studied Fourier, right? You studied Fourier? What Fourier was saying? Infinite harmonics. So here, this rectangle, okay, if you see it in the frequency domain, it will be a sink that will go to infinity or minus infinity. And what happens with infinity? We engineers, we hate something infinity. The people studying math, they like infinity, but we engineers, we say this is not practical. So I need it to be practical. I cannot do infinity. Okay, so I have to control the signal. So whenever you have this cut of the sink, what will happen to the rect? Trim. Okay, so the rule that you have seen, you all finished your signal system, right? But it does not look like, you know, good. I will always assume, you know, you are the best in math or physics or signals and systems or what else? Probability and statistics, programming, ethics. What else? I said math. This was first one. Don't worry, they will add up. Okay, good. So the rect, whenever it will go to a frequency domain, it is a sink. Whenever you cut the sink, so here we call it a trimmed sink, it will be a rolled off rect. What is a rolled off rect? Rounded like this. So in a practical system, this will never happen. This is the one that is implemented. Cool. Hamza, lost? مش فاهم عليك.
بعد ما عملنا فوري ترانسفورم للسينك دايركت للسينك بعدين صار انفرس فوري صح؟ شو اللي صار بعدين؟
Here we have, this is the rect. Okay, it's Fourier transform as a sink. Okay, the sink goes to infinity or minus infinity. We cannot afford infinity minus infinity engineering, okay? So we have to cut. So now it is not a perfect sink. It's a sink that has been removed some part of it. Some harmonics in terms of math, or some replicas in terms of engineering. Good? هذول called harmonics or replicas. Good? فهذا السink now it is a smaller sink. It does not go to infinity minus infinity. It will go from F1 to F2. This is what we call a trimmed sink. It's called a trim. What does trim mean? It has been cut. Trim sink. The trim sink, whenever we do its inverse Fourier transform, its Fourier transform, the time domain, it is not a rect. It is a rolled off rect. And it is not accurate here. It's not sharp. Okay? But it has some, this is called rolled off. Okay? So we have some curve. Answer? Sure? This is why I said that in theory, this is the G of T. In practice, this is the G of T. Good? Sure so far? Questions? If I want the energy for S1 of T, how much it will be? Area under the curve. Good. Okay? Or, in terms of math? Sorry? Integration, okay? From 0 to capital T here. Good. Perfect. So here we will square this one. And we will put the energy of G of T. Because the energy of G of T will include the T. Good? So in order to make our life easier, they normalize this one. They want to normalize this one. So what do you mean normalize? But yeah, it means we want it to be 1, its energy. So if you want to normalize, so I want its energy to be 1. So looking now here to the G of T, if I want the energy to be equal to 1, what should I do? Sorry? I need an answer. That's it. So here the amplitude is 1 over capital T. So if I make the amplitude to be 1 over capital T, now the area under the curve will be equal to 1. So the energy will be equal to 1. Good. Then now I will only focus on A1, A2, A3, A100, A whatever. Cool? Clear this point? Sure? Questions? Yusuf? What is the other Yusuf? ضايل 5 دقايق. يوسف. وخالد مسنج. مين عمر؟ عمر. Good. So, what else we have to comment here about the energy? شو اللي صار؟ Okay. From math, whenever I have a point here and you are asked to obtain its energy, how you do it? It's a point. What? Yeah, distance squared. So here the energy is equal to the distance squared. Based on that, where is S1, S2, S3? So S1, S2, so here we have them like this. So this was S1, 1 watt, right? Can't S1 here 1 watt or S4 1 watt? S4 can't 1 watt? Yes, good. S4 the 1 watt, but then 0.75, وبعدين 0.5 و 0.25. S4, S3, S2, S1. Based on that, okay, why I will waste energy? They said we have a better setup, which is (0.125 watts minus 0.25 watts minus 0.375 S4, S3, S2, S1. And here is 0. Yes, I will come to this negative power. So what they have done here, okay, regardless of the negative power, I will come to it. Okay, so we have put, because where was the 0 here? The 0 is here. They have put the 0 in the middle. Okay, so they centered the 0 and they made the symbols to be closer to 0. With which objective? Decrease the energy. Okay, so here, this setup, let's say call it setup A, this is setup B, here, setup A, setup B. The energy, both of them, they are the same, because here, how much is the distance between these two? 0.25, 0.25, 0.25, 0.25. So the probability of error has not increased. It's the same space between them. Okay, they are 4, 4. So 2 bits in each one of the symbols. So data rate is the same. So setup A and B, they A and B, they have same performance, data rate, error, and everything. Okay, but the energy here, but the energy of A is less than the energy of B. This is why it is senseless to use B. Okay, we will only use A, and there is no it depends here. Okay, it has to be used. Okay, this is engineering. Okay, so there is no trade-off. Always we say it depends. Whenever and it will improve something, it will make something worse. Okay, but here it's just improving. Okay, it's the same performance by just putting it properly. Okay, it will have less energy. So setup A is the one that is used. Why it is less energy? So the energy is the distance, but here distance from 0. So this distance squared with this distance, or this distance, or this distance, compared to this, or this, or this, or this. You see, it's closer. So because we put the 0, we center the 0 in the middle, so the distances to this 0 are closer, so the energy is less. Clear this point? So how to allocate or where to put the symbols? Are the symbols orthogonal? Check. Are they orthogonal? How do you know if they are orthogonal or not? 90 degree between them. Okay, good. 90 degree. Do they have 90 degree between them? If we multiply both of them, they will be 0. They are actually parallel, because one of them, each one of the symbols is, they have something common, which is the G of T. So each one of them is a value multiplied by this. It's a value multiplied by this, value multiplied by this. So they are like upgrades of each other. So they are not orthogonal. So here the system, where can I write it? PAM is not orthogonal. If it is not orthogonal, then we don't have phi 1 or phi 2, phi 3, and so on. Actually, we have one phi. So here, call it phi of t. There is no space. We will have here phi of t, and here the 0, or S1, or S2, whatever you want to call them. They were called what? S1 al-Asghar. Okay, so S1, S2, S3, S4. Good. And the distance between them, how much here? It was 0.25. To make it general, this is D, this is D, this is D. Good so far? Ali, lost? Hamza. عبيدة. Yeah. Irzam. You follow us? Sure. Questions? Shab. Okay. Yes. Which one? The non-orthogonal? Okay. So whenever we have orthogonal, so whenever we have two signals that are orthogonal, then S1, okay, multiplied with S2 should be equal to 0. This whenever we define orthogonal. Good. So now here, if I take S1, S1 is A1 G of t multiplied by A2 G of t. The answer will be A1 A2 G of t squared. If G of t is normalized, so it will be 1. So this is equal to A1 A2, which is impossible to be 0. Okay, so here the S1 or S2, they are if the G of t is a rectangle, so they are just an improved shape or a larger shape of the rectangle. But yeah, they are very correlated. They are not orthogonal. Yeah, but not orthogonal from the shape and not orthogonal here from the math. Clear? Here, so I can write they are not orthogonal. What was the benefit of the orthogonal if I have them orthogonal? What would be the good or bad, ya Khaled? The other Khaled. What? That's it. So here, if they were orthogonal, they would have our life to be easier. There will be no interference, so they will be much better. But yeah, it's good. So here, these are the ones. I will leave this one to the next time, but there's something that I forgot here. Why I have chosen rectangles? They could be triangles. Okay, so the shape could be anyone. This G of t. G of t, it could be rectangle, but also it could be triangle. Good. If it is triangle, where is the shape? The one that was transmitting. This one. If they have to be rectangles, okay, let me choose another color. So here it will be this one, this one, this one. And based on the amplitude of that rectangle, okay, we will know what is that symbol.
Can it be
any shape? In theory, it can be any shape. In practice, rectangle. Can be triangle, yani for specific cases, but yani 99% of the cases it is rectangle. Next time, I will describe more about this one, the line that I have drawn, or then I will see what happens with this 5 and why it is rectangle. Questions? Questions? No? So we stop here and see you on Monday, inshallah.